Hello everyone, this is Maverick Pua, the chemistry guru. Now in this video, we want to go through the suggested solution for 2024 A-Levels H2 Chemistry, Paper 1, question 1 to 10. So let us take a look at question 1. Question 1, I have cation X has the same number of neutrons as protons. X and an atom of neon have the same number of electrons. What is cation X? And we have four options, A, B, C, D. And we will go through and determine which is the answer. So the topic tested in question 1 is under atomic structure. Now, first thing first is, since the question mentioned that this is a cation, which means that X has to be positively charged. And if you run through A, B, C, D, A, it is a O2 minus, which is an anion. B, it is a F minus, which is also an anion. So straight away, we will be able to eliminate option A and option B. We are left with Na plus, which is a cation, Mg2 plus, which is a cation. So we are eliminating A and B straight away. Then question also mentioned that X has the same number of neutrons as protons, and X and an atom of neon have the same number of electrons. Of course, neon, we can determine that it has 10 electrons from the periodic table. And now we can do some comparison involving C and D. C, which is Na plus. So the mass number is given sodium 23. The proton number is 11. Involving Mg2 plus, the mass number is 24. Proton number is 12. So based on this, we can work out the total number of protons, the total number of neutrons, and the total number of electrons, and we can do comparison. So for Na plus, option C, the proton number is 11. The neutron number will be the mass number minus the proton number, which is 12. Number of electrons, since it is Na plus, so sodium atom will have 11 electrons, lose one electron, and I'll have 10 electrons. So this is the total number of protons, neutrons, and electrons for Na plus. For Mg2 plus, the proton number is 12. Neutron number is 24 minus 12, which is 12. The number of electrons will be Mg2 plus. So magnesium atom has 12 electrons. You take away 2 electrons, it has 10 electrons. So now we are able to look at the question and we determine our answer. Question mentioned that X has the same number of neutrons as protons, which is the case for Mg2 plus, option D. Both proton number and neutron number is 12, and X and an atom of neon has the same number of electrons. So neon has 10 electrons. We've talked about it earlier. Both Na plus and Mg2 plus have 10 electrons. So either one of them fulfill the second criteria. So since we need both of the criteria to be valid, same number of neutrons and protons, and the number of electrons for X and electrons are the same. So therefore, only option D is correct. Answer to question 1 is D. All right, next, let's move on to question 2. Which statements about the bond energy of single covalent bonds are always correct? Statement 1, a longer covalent bond results in a greater bond energy. Statement 2, a larger nuclear charge on the bonded atoms results in a greater bond energy. Statement 3, a greater attraction between the shared pair of electrons and the nuclei of the bonded atoms results in a greater bond energy. So we want to decide which of the statements are always true. So the topic tested in this question is atomic structure, also a little bit of chemical bonding because we will need to know what is defined as a covalent bond. Let's talk about each of these statements part by part. So statement 1, a longer covalent bond results in greater bond energy. Of course, first thing, we need to understand what do we mean by a covalent bond. So covalent bond is the attraction between the bond pair of electrons and the two nuclei that is sharing this bond pair of electrons. So essentially, it is the attraction between two nuclei and the bond pair of electrons. So if we consider a covalent bond that is longer, then would it result in greater bond energy? That means the covalent bond is stronger. So we have these two examples here. First one is when X bonded to Y. Let's say X and Y, they are both nuclei. So X is bonded to Y and the bond is shorter. So again, we've mentioned that the covalent bond, it is the attraction between the nucleus X attracting this bond pair of electrons and the attraction involving nucleus Y and this bond pair of electrons. So there's a combined attraction between X and bond pair, Y and bond pair of electrons. That will be my covalent bond. And we notice if the bond is shorter, the bond pair of electrons will be closer to the nuclei. And since they're closer to the positive nucleus, attraction is supposed to be stronger. And therefore, if the covalent bond is stronger, then the bond energy should be higher. So conversely, if I have X bonded to Y and the bond is very long, you notice the bond pair of electrons is very far away from the nuclei. And this will mean that if the two electrons, they're very far away from the nuclei, attraction will be weaker. And this will mean that bond energy is smaller. That means the longer the covalent bond, actually the covalent bond will be weaker and the bond energy will be smaller. So statement number 1 is not true. Statement number 1 is false. Now, how about statement number 2? Now, statement number 2, I have a larger nuclear charge on the bonded atoms will result in greater bond energy. So is that true or not? Now, we have to be careful in terms of the difference between nuclear charge and effective nuclear charge. So involving my nuclear charge, it is just purely based on the number of protons. All right, because the nuclear charge is just based on the charge of the nucleus. If I have more protons, then I'll have a bigger nuclear charge. And by right, when you have a bigger nuclear charge, I will be able to attract the electrons more strongly. But on top of that, the attraction on my valence electrons actually will also take into consideration other things, such as the distance from the nucleus and the shielding effect. So I think let's use this as an example. The bond energies involving your hydrogen halide, HF, HCl, HBr, Hi. I put this from the data booklet. We have this information inside the data booklet. And the bond energy is given 500 plus, 400 plus, 300 plus, 200 plus. So you notice, if I consider HF, the bond energy is higher. Hi, the bond energy is lower. And what I've done is I've picked up the proton number for my halogen, fluorine, chlorine, bromine, iodine, because we want to target the nuclear charge, which is the number of protons, right? So fluorine has 9 protons, chlorine has 17, bromine has 35 protons, and iodine has 53 protons. So if statement 2 were true, this would mean that involving iodine with so many protons, right, 53 protons, then the nuclear charge clearly is bigger. You have a bigger nuclear charge because you have so many protons. So does it result in a greater bond energy? Actually, that's not true. When you have, for iodine, a very big proton number, the bond energy actually is lower. So this means that the bond energy is actually not only due to nuclear charge. Nuclear charge is just part of the factors, and we also have to consider other things, such as the shielding effect and the distance from the nucleus. So we want to at least take note, okay, in this case, the nuclear charge increases for my halogen, but the bond energy drops. So the attraction of the bond pair of electrons is not only affected by nuclear charge, it's affected by effective nuclear charge. ENC is effective nuclear charge. So under atomic structure, we've learned that effective nuclear charge is nuclear charge, which is based on the charge of the nucleus, how many protons you have, shielding effect, and the distance from the nucleus. Now, shielding effect and distance from the nucleus, they're related to each other. So if you're in a bigger principal quantum number, if my valence electrons is in a bigger principal quantum number, then you'll be further away from the nucleus. And if you're further away from the nucleus, the attraction to the nucleus will be weaker because you're further away, attraction is going to be weaker. On top of that, if you're in a bigger principal quantum number, then your shielding effect will also increase because the number of filled inner shell that can block the attraction between the nucleus and the valence electron will also go up. So we have to take into consideration the effective nuclear charge. Effective nuclear charge, it is the overall attraction between the nucleus and the valence electrons. That's a much better measure involving the attraction on my valence electrons. So this is number 2. Statement number 2 is false. It's not true. Statement number 3, greater attraction between shared pair of electrons and the nuclei of the bonded atoms results in a greater bond energy. Now, if you look at this statement, attraction between shared pair of electrons and the nuclei of the bonded atoms is essentially the definition involving my covalent bond. So the statement 3 is trying to say that if you have a greater attraction for this covalent bond, you have a stronger covalent bond, then you result in greater bond energy. Obviously, this is true because bond energy, it is the energy required for me to break my covalent bond. So if the covalent bond is stronger, so this will mean that I'll need more energy to break this bond. So statement number 3 will always be true. So we have our conclusion here. Statement number 1, longer covalent bond results in greater bond energy. That's not true. Statement number 2, larger nuclear charge results in greater bond energy, which is also not true. Statement number 3, your greater attraction between the shared pair of electrons and the nuclei of the bonded atoms result in greater bond energy. Statement number 3 is true. So this means that for question 2, answer will be D. All right, next, let's take a look at question 3. Number 3, the boiling points of H2O, H2S, and H2SE are different. H2S has the lowest boiling point, so this is given. So which statements are correct? Number 1, H2S has a lower boiling point than H2SE because H2S molecules have weaker permanent dipole forces of attraction. Number 2, water molecules experience weaker temporary dipole-induced dipole forces of attraction than H2SE molecules. Number 3, water molecules experience stronger permanent dipole forces of attraction than H2S molecules. So we want to decide which of the statements are correct. So let us take a look at this question. The topic tested in this question 3 is intermolecular forces. So number 1, my H2S has a lower boiling point than H2SE because it has weaker PD-PD forces of attraction. So this statement is not true because the permanent dipole interaction, it is related to the polarity of the bond and overall the polarity of the molecule. So if I consider sulfur versus selenium, sulfur is higher up in the periodic table. It will be smaller in terms of size. The electronegativity will be higher. So oxygen is more electronegative than sulfur. Sulfur is more electronegative than Se. Sulfur is more electronegative than Se in this case. So this will mean that HS bond will be more polar than HSE bond. If you're more electronegative, then the difference in electronegativity between sulfur and hydrogen will be bigger as compared to selenium and hydrogen. So the bond will be more polar. So HS bond, if it is more polar, then it will also mean that my H2S will be more polar. It is a more polar molecule than H2SE. So this would mean that the permanent dipole interaction for H2S is supposed to be stronger. But the question tells me that H2S has the lowest boiling point, and the reason why it has the lowest boiling point is when we do comparison between H2S and H2SE, the intermolecular forces that will be used to explain the difference in the boiling point will be based on your ID-ID interaction due to electron cloud size. So involving H2S, it has the lowest boiling point, or it has a lower boiling point than H2SE because it has a smaller electron cloud size. Selenium is bigger than sulfur. So H2S will be smaller electron cloud size, less polarizable. So the ID-ID attraction will be weaker. So if ID-ID attraction is weaker, then this will mean that the boiling point will be lower. So to explain H2S has a lower boiling point than H2SE, we should be using ID-ID interaction rather than permanent dipole interaction. Anyway, statement number 1 is not true. Your H2S molecule, it has stronger PD-PD interaction as compared to H2SE. It is just that the ID-ID interaction is dominant because your H2S has a lower boiling point than H2SE. So we should be using ID-ID interaction to explain the outcome rather than permanent dipole. So therefore, statement number 1 is false. Now, how about number 2? Now, number 2, it is a little bit tricky, involving water molecules experience weaker temporary dipole-induced dipole forces of attraction than H2SE molecules. Now, some of us will call this instantaneous dipole-induced dipole interaction. Dispersion forces, van der Waals forces, they mean the same thing. Now, maybe when we consider water, we will say that water obviously is hydrogen bond, right? So water does not have temporary dipole-induced dipole interaction. Actually, that's not true. The idea involving ID-ID interaction is because of presence of an electron cloud and because of the fluctuation of the electron cloud. And therefore, at any instance, your electron cloud will be distorted, and there's a little bit of dipole moment associated with that. The random fluctuations of my electron cloud will result in my temporary dipole. So as long as you have an electron cloud, you will have some degree of ID-ID interaction, including polar species like water. Water, we know that dominant intermolecular interaction is hydrogen bond. Usually we will talk about hydrogen bond for water, but water will have some degree of ID-ID interaction. Of course, the properties of water is not explained using ID-ID. ID-ID is not significant, but it still has temporary dipole-induced dipole interaction, still present. And in fact, in this case, when we consider water molecules experience weaker temporary dipole-induced dipole attraction as compared to H2SE, that's true. Because water molecules, it is smaller in terms of size. ID-ID is directly related to electron cloud size. So smaller in terms of electron cloud size, so less polarizable ID-ID, it is weaker. So statement number 2 is true, but it doesn't contribute to the difference in the boiling point of water versus H2SE. Water is supposed to have the highest boiling point here, right? So that's why maybe some of us will feel that involving water should be hydrogen bond. So statement number 2 is false. Then we will get this question wrong. So we have to be quite careful with that. There's nothing wrong with this statement. Water is smaller, yes, but less polarizable electron cloud. ID-ID is weaker. So as mentioned here, all atoms and molecules have ID-ID attraction because of the presence of the electron cloud, random fluctuations of my electron cloud. So including discrete atoms, my noble gas atoms, all of them have ID-ID attraction. As long as you have an electron cloud, you have ID-ID. And it's purely based on size. Bigger electron cloud, the ID-ID is going to be stronger. Okay? Then next one is water will still have a higher boiling point as compared to H2SE because the dominant intermolecular interaction for water, we understand it is my hydrogen bond, which is very, very strong. So statement number 2, interesting. Statement number 2, it is true. How about number 3? Now, statement number 3, water molecules experience stronger permanent dipole forces of attraction than H2S molecules. Again, some of us might feel that it's not PD-PD, it is hydrogen bond. But you have to remember, hydrogen bond is just a very, very strong version of permanent dipole interaction. The nature of PD-PD and hydrogen bond, they are exactly the same. I have a bond that is polar, so therefore the entire molecule is polar. So when you have attraction between a permanent dipole and another permanent dipole, then the attraction, usually we will call this PD-PD, but involving molecules that contains HF bond, HO bond, HN bond, because these 3 bonds, HF, HO, HN bond, is so polar, is so strong that we give that PD-PD interaction a special name. We will call this hydrogen bond. So you have to be careful. A hydrogen bond is just a very, very strong permanent dipole interaction. In fact, we will reserve hydrogen bond for the 3 most polar bonds that we have. HF bond, HO bond, HN bond. Molecules that contains either of these 3 bonds. Okay? So statement number 3 is true. Because oxygen is more electronegative than sulfur, so OH bond more polar than SH bond, which means that water is more polar. So water should have a stronger permanent dipole attraction. Again, the PD-PD attraction is so strong that we give it a special name. We call it hydrogen bond. But hydrogen bond, again, is just a subset or a very strong permanent dipole interaction. So this question, I think statement number 2, statement number 3 is a little bit tricky. Some of us, maybe if we don't think too much about it, then we might jump to conclusion, thinking that some of the statements, number 2 or number 3, it is not true. So we have to be quite careful with that. So which of the statements are correct? Number 1 is wrong. H2S doesn't have weaker PD-PD interaction. Number 2 is true. Your water actually has weaker temporary dipole-induced dipole interaction or instantaneous dipole-induced dipole interaction. Number 2 is okay. Number 3, water has stronger PD-PD attraction as compared to H2S. That statement is also true. So number 2, number 3 are correct, and therefore answer to this question will be C. Okay, how about question 4? Question 4, the zwitter ion of amino ethanoic acid is shown. Structure is given. What are the bond energies, X, Y, Z in this structure? A very classic question, super easy as well. The topic tested in this question, of course, is under chemical bonding, specifically the shapes of molecules according to the valence shell electron pair repulsion theory. So what we need to focus on is the central atom. We consider the total number of lone pair plus bond pair, and then what is the shape and what is the bond angle. So with respect to nitrogen, this guy is 4 bond pair, no lone pair. So shape is tetrahedral, bond angle is 109.5. So X is 109.5. How about C, the blue carbon here? Now the blue carbon here, the number of lone pair plus bond pair is exactly the same as nitrogen, 4 bond pair plus no lone pair. It's also tetrahedral. Bond angle is also 109.5. So bond angle Y is also 109.5. Then the orange carbon, which is 3 bond pair, no lone pair. Remember, double bond also counted as 1 bond pair. For valence shell electron pair repulsion theory, single bond, double bond, triple bond, they're all counted as 1 bond pair of electrons. So in this case, this is 3 bond pair, no lone pair. The shape is trigonal planar. Bond angle is 120. So Z bond angle should be 120. So very straightforward exercise here. X and Y are 109. Then Z is 120. Answer to this question is D. Okay, how about question 5? Consider the atoms of the period 3 elements from sodium to argon. What is the total number of single unpaired electrons in the valence shells of these 8 elements? So the topic tested for this question is under atomic structure, basically just writing out electronic configuration. So it's a little bit troublesome, but we just want to, again, be careful with what is the question asking. The question is asking the total number of single unpaired electrons in the valence shells of these 8 elements. So for each of these elements, sodium all the way to argon, we're going to write down the electronic configuration. And what I've done is I have also written the electron in box diagram for my valence shell. So to be very clear, involving how many unpaired electrons we have. And once we have that, then we just go and count the total number of unpaired electrons. So it is more tedious than difficult. So just in case some of us, maybe we are not drawing out the electron in box diagram, then again, we have to be very careful in terms of how many unpaired electrons we have. So the idea is this. I write out the electronic configuration for each one of them. Sodium with 11 electrons, 1s2, 2s2, 2p6, 3s1. Should be fairly straightforward. Now, this one we should be able to write down very fast, but it's a bit tedious. We have to write down all of them. Of course, we can just, based on this, we can just extend the electronic configuration for the rest of the elements. But for each of the element, what we will have to consider is which one of them has unpaired electron, and we just take note of the number, then we just add everything together. So in terms of presentation, what I've done is I've just written everything, so it's easier for us to take a look, easier for us to count. All right. So the valence electron is 3s1. 3s1, of course, there's 1 unpaired electron. Then magnesium, it is neon 3s2. I write this as square bracket neon, which will represent the electronic configuration for neon, obviously, 1s2, 2s2, 2p6. So to make it a bit more concise, neon 3s2. So 3s2 is something like this. Of course, this is paired. Aluminum 3s2, 3p1. So 3s2 is fully filled, 3p1. I have 1 unpaired electron. Silicon 3s2, 3p2. 3p2, remember Hund's rule. I will need to fill up the p orbitals singly and with parallel spin. So 3p2 is something like this. I have 2 unpaired electrons. All right. Phosphorus 3s2, 3p3. 3s2 is fully filled. 3p3, I have 3 unpaired electrons. Then sulfur 3s2, 3p4. Then 3p4, I'll start to have electrons pairing up. I'll have 2 unpaired electrons. Chlorine 3s2, 3p5. I'll have 3p5, I have only 1 unpaired electron. And argon, obviously, this is a noble gas, so 3s2, 3p6, and it is fully filled. There are no unpaired electrons. So what I've done is I've highlighted the number of unpaired electrons, then we're just going to count them. So I have 1 from sodium, and then 1 from aluminum, 2 from silicon, 3 from phosphorus, 2 from sulfur, 1 from chlorine. Add everything up, I will have 10 of them. All right. So answer to this question will be B. Okay, next, let us move on to question 6. Use of the data booklet is relevant to this question. Percentage composition by mass of some compounds is given. In which compound does silicon, phosphorus, or sulfur show its highest possible oxidation state? So involving A, I have a chloride of phosphorus, 77.5% by mass of chlorine. B, I have oxide of silicon, 53.2% by mass of oxygen. C, your oxide of phosphorus, 43.6% by mass of oxygen. Then D, involving your sulfur oxide, 49.9% by mass of oxygen. Now, the calculation is actually not very difficult. It's under mole concept. And what we will do is, based on the mass analysis, based on the percentage mass of the two elements, then what I do is I work out the number of moles and I work out the ratio, try to figure out the formula involving the compound, and then from there I can figure out oxidation state involving phosphorus, right? So let us do this part by part involving A. When you have chloride of phosphorus with 77.5% by mass of chlorine. So mass of chlorine is 77.5%. Mass in 100 gram will be 77.5. Mass in 100 gram for phosphorus will be 22.5. 100 minus 77.5, 22.5. After that, we will divide this by its atomic mass, and I'll get the number of moles. For phosphorus, the number of moles is 0.7258. Chlorine is 2.183. From there, we find the simplest ratio, 1:3. So 1 phosphorus to 3 chlorine, formula is PCl3. Oxidation state for chlorine should be -1 because it's more electronegative than phosphorus. So oxidation state for phosphorus here, in this case, will be a +3 oxidation state. Later, we will compare with the maximum oxidation state one shot. We will discuss this in a while. Involving B, outside of silicon contains 53.2% by mass of oxygen. The working is exactly the same. Oxygen mass in 100 gram is 53.2. Silicon, the mass will be 46.8, 100 minus 53.2, then divided by the atomic mass. Silicon number of mole is 1.665. Oxygen is 3.325. I find the ratio 1:2. Formula is SiO2, oxidation state for silicon. In this case, is a +4. Actually, we know that silicon maximum oxidation state should be a +4. So B very likely is going to be my answer here. All right. C and D, again, the working is exactly the same. It's just a little bit tedious. We have to do a bit of calculation. When you have 43.6% by mass of oxygen, then mass for phosphorus will be 100 minus 43.6, 56.4, divided by the atomic mass, 1.819 for phosphorus, 2.725 for oxygen. Ratio is 2:3. 2:3 means that the formula for your phosphorus oxide is P2O3. Oxidation state for phosphorus here, again, it is a +3 oxidation state. Then finally, involving oxide of sulfur, 49.9% by mass of oxygen. In 100 gram, I will have 49.9 gram of oxygen, then 100 minus 49.9, 50.1 gram of sulfur, divided by the atomic mass, 1.561 mole of sulfur, 3.119 mole of oxygen. Ratio is 1:2. So formula is SO2 oxidation state for sulfur is going to be a +4. So once we figure out all the formula and the oxidation state, then which compound does silicon, phosphorus, sulfur show its highest possible oxidation state? Silicon oxidation state highest possible is +4. Phosphorus is +5. Sulfur is +6. All right. So if I consider A, the oxidation state for phosphorus is +3. Actually, it is not the highest possible. It can go up to +5. So A is not true. B is my answer. Silicon oxidation state, it is +4, highest possible oxidation state. C, phosphorus oxidation state is +3, but it should be able to go up to +5. And then D, your sulfur oxidation state is a +4, but sulfur can go up to a +6 oxidation state. So answer to this question is a little bit tedious, but not super difficult. Answer to this question will be option B. Okay, next, how about question 7? The relative abundances of all the isotopes present in a sample of nickel are shown. So we have the relative abundance, and then we have the mass of isotope. And for 58, the relative abundance is 69.3. Then mass number 60, relative abundance 36.7. 61 is 1.20. 62 is 3.80. 64 is 1.00. Now, you have to keep in mind this is relative abundance. Relative to what? Relative to 64, because this is 1. Everything is relative with respect to the mass of isotope 64. Now, the relative atomic mass of nickel calculated from this data. It's actually quite easy. What I've done is I converted to table form because I think we're more familiar with the table form. So basically what we have here, I just tabulated. Okay, so these are the isotopic masses, 58, and their relative abundance. So 58, 69.3, 60, 26.7, 61 is 1.2, 62 is 3.8, 64 is 1.0. So for me to determine the relative atomic mass, it is just the weighted average. What we will do is for each of the isotopic masses, I'm going to multiply by the abundance, is weighted based on the abundance, then add everything up, whole thing divided by the total abundance. So it's just going to be 58 multiplied by 69.3, which is the first set. And then you plus 60 multiplied by 26.7, which is the second set, plus 61 multiplied by 1.2, plus 62 multiplied by 3.8, which is here, plus 64 multiplied by 1.00, which is here, then whole thing divided by the total abundance. Now you have to be careful in this case, because if you add up the total abundance is not equal to 100. Some of us might jump to conclusion, because for questions, it's quite common for the question to give us percentage abundance. Percentage abundance means that everything add up is equals to 100%. But now this one is not percentage abundance. This one is relative abundance, relative to this one, relative to the mass of your isotope, nickel 64. So this guy is 1, everything is relative to this guy, 1.000. So the total abundance add up need not be equal to 100%. And therefore, we have to be careful in terms of that. Because if, let's say, we jump to conclusion and we say that, oh, every time I just divide this by 100%, it's going to be the same. You didn't double check. You just whole thing divided by 100%. Then the numerator term is 5994.2. You divide this by 100, you're going to get 59.9. 59.9, actually, we have an option here. So if you choose C as an option, as an answer, then that is because you divide this by 100%. But the 100 is not the total abundance. If you add everything up, the abundance, it is actually 102. It is not 100. So this one, again, potentially we might make this mistake. So please be very careful with this. We want to be very sure. Involving the denominator, supposed to be the total abundance, we have to add everything up just to make sure the total abundance, rather than assuming that this guy is always equals to 100. Okay? So the total abundance is not equals to 100 because it is not percentage abundance, it is relative abundance. So if you use the correct denominator, which is 102, then the relative atomic mass calculated is going to be 58.8. Then answer to this question will be option A. Okay, how about question 8? Many metallic elements form peroxides containing the O2 2- ion as well as oxides. Oxide is O2-. Which compound has the least negative value for lattice energy? Least negative value is just that because lattice energy is always negative, it is always exothermic. When you form your ionic compound from your constituent gaseous ion, is always exothermic because heat is released. So least negative means that the magnitude, it is the lowest. The magnitude, it is the smallest. That means the ionic bond is the weakest. So the magnitude of my lattice energy will be the smallest. So we have 4 options: calcium oxide, calcium peroxide, potassium oxide, potassium peroxide. If we think about it, we only have 2 cations and 2 anions, Ca2 plus versus K plus. Oxide, which is O2- versus peroxide, O2 2-. So since we are looking at lattice energy, then we will use this expression that we learn under chemical bonding. So this lattice energy expression, it is proportional to Q plus Q minus divided by R plus plus R minus term. Q plus, it is the charge of the cation. Q minus, it is the charge of the anion, divided by the R plus, which is the radius of the cation, plus R minus, which is the radius of my anion. The denominator is just the distance between the cation and the anion. Some schools, maybe the way they term it, they might be using different symbols, but the expression is still the same. So lattice energy is proportional to this magnitude. The product of the charges of my cation and anion divided by the distance between the cation and my anion. All right. So we have 2 cations and 2 anions involving Ca2 plus versus K plus. The size is similar because they're in the same period, so size is roughly the same. Ca2 plus versus K plus, obviously Ca2 plus, the charge is bigger, plus 2 versus plus 1. Then O2 minus versus O2 2-, both of them, the negative charge is the same, so the Q minus is the same. And the difference between them, of course, will have to be the R minus. Oxide, it is smaller in terms of size because it's just one species, one atom. Then O2 2-, because you have 2 oxygen, is going to be bigger in terms of size. So the radius involving O2- will be larger. So question is asking for which compound has the least negative value for lattice energy. So the magnitude, in this case, the magnitude is supposed to be the smallest. So means that if I want the magnitude to be the smallest, the numerator, we want it to be as small as possible. The denominator, we want it to be as large as possible. So I want a small Q plus. So instead of calcium 2 plus, I'm going to choose K plus. K plus has a smaller charge. Numerator is going to be smaller. Then R minus, I want to choose the bigger R minus so that it would be giving me a bigger denominator. So I should be choosing K plus and O2 2 minus peroxide. So the compound that should have the smallest magnitude involving my lattice energy should be potassium peroxide. So answer in this case would be option D. All right, next, how about question 9? The decomposition of SOCl2 is a first order reaction. After 24 hours at a certain temperature, the concentration of SOCl2 decreases from 0.016 mole per dm cube to 0.002 mole per dm cube. So at this temperature, how long will it take for concentration of SOCl2 to decrease from 0.016 to 0.001 mole per dm cube? So the question mentioned first order reaction. They give us all this information. Basically, we need to determine the half-life. So the topic tested in this question will be under kinetics. And as mentioned earlier, question tell me that this is a first order reaction, which means that my half-life is a constant. Only for first order reaction, half-life is a constant. So half-life is the time taken for me to halve the concentration of my reactant. So if I start off with 0.016, then time taken for me to halve this amount to 0.008, this is a half-life. Time taken for me to decrease the concentration of your species from 0.008 to half of it, 0.004, another half-life. And then 0.004 to 0.002 will be another half-life. And 0.002 to 0.001 is another half-life. So question first tells me that decreases from 0.016 to 0.002, that's 24 hours, which is 3 half-lives, right? If you look at this diagram here, 3 half-lives for me to decrease the concentration for this guy from 0.016 to 0.002, which is 24 hours. So this will mean that each half-life, one half-life is 8 hours. Then now, if I want to decrease this from 0.016 all the way to 0.001, it will just be 4 half-lives. So very, very simple. So once I've determined my half-life, which is 8 hours, then time taken for me to decrease the concentration from 0.016 to 0.001 will just be 4 half-lives. So 4 times 8, that's 32. Answer to this question will be C, 32 hours. All right, question 10. Reactants P and Q are involved in a chemical reaction. In an experiment involving large excess of Q, the graph of concentration of P against time has a constant half-life. And then in further experiments, the rate of reaction is measured using different initial concentrations of Q. Results are shown here. All right, what is the numerical value of my rate constant? So basically, we need to determine the order of the reaction with respect to P, with respect to Q. Then we write out the rate equation, then we rearrange and solve for my rate constant. So the kinetics question in general are fairly straightforward, fairly standard. So topic tested, of course, is under kinetics. And first thing, let us try to determine the order of the reaction with respect to P. So question mentioned that in an experiment involving large excess of P, concentration of P against time, the graph of concentration of P against time has constant half-life. So the purpose involving large excess of Q is if I have a large excess of Q, then the concentration for Q will be a constant because the change of it is negligible. So this would mean that Q doesn't affect the rate of the reaction, and we can have a direct comparison involving P and the order of the reaction and how P affects the rate of the reaction. So in this case, since the concentration of P against time, the graph has a constant half-life, then this would mean that it is first order with respect to P. So order of the reaction with respect to P, you can determine is order 1. This is order number 1. Then next one, we want to determine order of the reaction with respect to Q using this table. I have 2 different experiments, and the concentration for P, you notice, stays the same. So now what I have is I have 2 experiments. The concentration of P, I keep it the same so that it doesn't affect the rate of the reaction. It doesn't affect the initial rate of the reaction. Then my Q concentration from 0.025, I increase it to 0.0600. The concentration increases by 2.4 times. And then there is a change in the initial rate from 4.76 times 10 minus 4 to 2.74 times 10 to the power minus 3. It increases. And it actually increases by a factor of 5.76 times, which is 2.4 square times. So this means that when you change the concentration of Q by 2.4 times, the rate of the reaction increases by 2.4 square times. This will suggest that it is second order with respect to Q. So once I've determined order of the reaction with respect to P is order 1, order of the reaction with respect to Q is order 2, I can write out my rate equation. Rate equals to rate constant K, P concentration power 1, Q concentration square. So the rate equation is here. Of course, the next thing we have to do is the question asks me solve for K. I rearrange it in terms of K. Rate constant Ka equals to rate divided by P concentration and Q concentration square. Substitute the value from either experiment. It doesn't really matter which one. So we're going to use the values for reaction number 1. Reaction number 1 or experiment number 1, P concentration 0.002, which is here. Q concentration is 0.0250, which is here. And then the rate is 4.76 times 10 to the power minus 4, which is here. So I simplify this guy. I will be able to solve for K. K is 38.1. So answer to this question will be C.